Hi, this video is on the central limit theorem. This is section 11.5 from Monday. This is probably the most important theorem in statistics. Um, we're able to have a lot of results because of it, do hypothesis testing, confidence intervals. So based on what we do today, we'll be able to do some statistical applications on Thursday. And then tomorrow, we start test two, so you just have a day to work on that, ask questions, and then we'll get back to doing a few more sections, and then we're done. So the central limit theorem, the animations I had in Maple, I think, show pretty strongly that, again, you add enough any random variable, you get back to a nice bell-shaped curve. So yeah, the central limit theorem is the topic 11.5. This was the outcome. The sum of a large enough number of any independent random variables is a normal distribution. I showed you the uniform continuous, the uniform discrete. The exponential, I can show you for a minute here, it is still running. So I don't know if it will, maybe let it run all night, maybe I'll finish it. So trying again today. How can we prove this, that a large enough sum of any random variable is normal? We just use moment generating functions. It's really nice. It's in the text, and I can email you, talk through it if you want to see it as well. Let's go down. It really is probably one of the most important results in probability and in statistics. Here's what we did the other day. Actually, this is in 11.2. If we add a bunch of random variables, it doesn't matter if they're whatever they are, if they're independent of each other, have the same distribution. If we add them all up, if we subtract off the mean of the sum and divide by the standard deviation of the sum, then we'll get a nice normal curve. So that's what this is saying down here. You take the sum of them, subtract off the sum of the means, subtract off the standard deviation of the sum, then you can approximate it with really a standard normal. So this would be our z-score. Or you can integrate, that's what this is doing right here, but we can use tables too. We're going to make a slight change to this when we do, we're talking about the average of a bunch of random variables. That's just going to be this formula here divided by n. So you'll see it'll just change slightly to give us the result that we're going to use a lot in 11.5. Here are two more examples that we're adding random variables. So the weight of a certain probability book is normally distributed, so let's call x the weight, and it's normal. Well, yeah, it is normal with a mean of 3 pounds and a standard deviation of 1 pound. Okay, this is probably the random sample of 10 probability books will weigh more than 25 pounds. So they might not all weigh exactly 3 pounds, so they come from a normal curve. The weights will be somewhere in here, 3 pounds plus or minus a pound. What's the probability? I add 10 of them together, so let's let W be the total weight of x1 plus x2 plus x10. Those, the total weight should be normally distributed. The mean of this should be the mean plus the mean plus the mean plus the mean, so that's going to be 3. 3 is the weight. 10 of those will be 30 for the total weight. And I'm allowed to add I'm not allowed to add standard deviations. I'm allowed to add variances. So variance plus variance plus variance plus variance. So that's going to be 1 squared, 1 squared, 1 squared. So 1 squared, 10 of those. And then I'll take the square root for the standard deviation. So the total weight is normally distributed with a mean of 30, and this is the standard deviation. So now I want to figure out what's the probability that the 10 books together weigh more than 25 pounds. And so I'm just going to standardize again. So this is a z-score, 25 minus 30 divided by square root of 10. That's the probability that z is greater than, and I get, again, a value. I'm going to use my z-table, look it up in the z-table, and that's the probability. So if you need to be reminded about how to do this, let me know. I'm just assuming back when we did section 7.2, everything was fine. Here's another problem. Yeah, so what if the weights of the books were, if they don't have to be normally distributed to use a central limit theorem, because we know the sum of normals is normal from moment generating functions. If the weights of the books were uniformly distributed, yes, the central limit theorem would still come into play, because you saw on a previous video, if you sum even a couple uniforms, you get back to a normal. So definitely, if these were uniformly distributed, I would still be back to a normal distribution. So example 2, wait times at Taco Bell for lunch are exponentially distributed with a mean of 5 minutes. So here are wait times. This is t, f of t, here and here's 5 minutes. We know that f of t is 1/5 e to the negative t over 5 for t bigger than 0, because that's the distribution for a exponential distribution. What's the probability that total wait times for 100 selected cars is less than 495 minutes? I know that's kind of a crazy question, but each driver we expect to have this as their distribution, about 5 minutes. So if I add together 100 wait times, so this is a wait time for car 1, wait time for car 2, wait time for car 3, wait time for car 100, if I add 100 exponentials together, for sure it's normal. So we're going to say that's normal. With a mean of, let's see, this is going to be 5 minutes, 5 minutes, 5 minutes, 5 minutes, so 500 minutes. And let me see, variance, right, expected value is 5, and variance of t is 5, right, for an exponential. So 5, 5, 5, 5, 5, 5, so 100 times 5, and then I take square root to find standard deviation. So now to find the probability, I don't think I have any more room. Oh yeah, I do. So to find the probability that the total wait time is less than 495, I'm just going to convert again. Guess the probability z is less than 495 minus 500 divided by the square root of 500. I get a z-score, go to the table, etc. Okay, so I think that's good. I'll do the next part. Now we're going to look at the distribution of x bar instead of the sum of x's. Instead of saying what's the probability that the total time is, less than 495 minutes, I'm going to say what's the probability that the average time, so if we took 100 cars and we average their total time, it's the same question pretty much, except we're asking about averages instead of sums. So there's just a slight difference. So I'll show you that in the next video.